We're going to be doing the same stuff we did on the last video, except this time we don't know the value of sigma. So what we'll use in place of sigma is S, the sample standard deviation. So when sigma is not known, use the sample standard deviation. Plus, use the T table. That's right, there's another table to be used here instead of the normal distribution. Let me see if I've got it handy. Here is the cumulative probability table for the T distribution. You can see we're going to do a few problems to figure out how to get information here. But these T values are replacements for Z. And these values in here are not necessarily, well, they're not areas, but they're valuable in helping us determine areas that are in the tail ends of this distribution. The good thing about it, though, is basically it looks just like a normal distribution. It's even centered at 0. The only thing different, a normal distribution might be a little bit off by a little bit. I'll give you an example here. We'll go into Desmos, and I'll show you what the difference is in there. So there's the normal distribution. And the T distribution requires something called degrees of freedom. I'm going to put in a number. Now, it looks like they're exactly the same, these two graphs, but let me zoom in so that you can see there's gap. The red one is the normal distribution, and the blue one is this T distribution, this T table. So you can see they're a little bit different. What happens is this. As you increase what they call the degrees of freedom, which is also decreasing the sample size, look what happens. It gets a little closer. And then if I come back up, let's make it even 20, you'll see it gets even better. See, it's even closer then. We often say that 30 is something of the cutoff for when you want to just start using the normal distribution, because 30 or more of sample sizes is guaranteed. So look what happens when I change it to 30. They practically look like the same curve. So the T distribution is able to be used here. There are certain nuanced mathematical things that are involved with this table that I can't really show you, but we can work with the table and know that you must, when you don't know the standard deviation, you must go with the T table. All right, so here we have an alpha level. We have the degrees of freedom. I'll talk about what those mean in just a minute. And we have a right-tailed t-test. So all these things are important. The alpha level is important. The degrees of freedom are important. And whether it's a one or a two-tailed test will be important. So let me go ahead and pull up the table and see if I can find this out. So I'm going to look where degrees of freedom is 16 and alpha is 0.05, one-tailed test. So let's come back up here. So I want my alpha. These are the alpha levels here at the top. We want to go along this one tail. So here I go until I get to 0.05. So this is my column right here. This actually lists T95. I think I understand what that means. So if we come down here, now I'm going to go to where the degrees of freedom is 16. And look where these two meet, 1.746. Okay, so first of all, let's track down our alpha level. That's this one right here. So there's my column. The degrees of freedom is 16, so there's my row. And let's find out where the column meets the row. So our critical t value then is t equals 1.746. Similar problem. Degrees of freedom this time is 21. Left-tailed is important because that means the t value is going to be negative. The previous one was a right-tailed test, so we knew it was positive. This one is a left-tailed test. That means we got to keep in mind that we're dealing with negative value once we look this up. So degrees of freedom 21, alpha is 0.05. All right, I brought up the relevant portion of the table. Degrees of freedom, alpha equals 0.05. So there's our 0.05. It's a one-tailed test. So we take the top numbers, and the degrees of freedom is 21. I went a little too far on that one. So we get 1.721, but be careful, because it's a left-tailed test, t is negative 1.721. Next, alpha is 0.01, degrees of freedom 14, and two-tailed test. So you don't have to do much dividing or anything like that. The table is structured to handle this kind of problem right off the bat. Let me pull it up. And let's see if we can find our 0.1. Now you got to watch here. Here the alpha level is underneath because we're looking for two tails this time. So my column is not 0.01 here, it's 0.01 over to the right of that. And then our degrees of freedom is 14, so that's this number here. Let's see where we intersect. Oh. .977. So in a two-tailed test, you have this. So you actually get two t values doing that. Now we have alpha is 0.10. Degrees of freedom is only 8. Right-tailed test, so you know that t is going to be a positive number. Alpha equals 0.10, so there we are. This is a one-tailed test. Degrees of freedom is 8. And since we're on the right side, we have a positive value of t. T equals 1.397. There are only two assumptions that we're going to make when we're dealing these problems. One, and this is the first assumption for all of them, the sample is random. And two, we need n to be at least 30, or, on the other hand, n is less than 30, and the population is approximately normal. How do we do p-values in this class? Let's take an example. T equals 2.787. Degrees of freedom equals 25. Let me get the p-values for these numbers. All right, so what you do, you try to look throughout these values within the table. You'll notice you find 2.787. So that's across from the 25. And we have two different values here, or well, two different alpha levels. So for one-tailed test, we have the p-value equals 0.005. If it's two-tailed, the p-value equals 0.01. So up here, these two guys here are where the well, actually I circled too much there. The p-values are going to be one of these two numbers here. These will be my p-values. Now I chose this one purposefully because it had a direct answer here. Many times you're going to find that you fall between the values. All right, we have a medical investigation claims that the average number of infections per week in a hospital is 16.3. The word is used, so we're going to have a setup like this. And then, of course, the not equals version always goes into HA. And let's see what we have here. We have a mean number of infections. How many were sampled here? Oh, 10 weeks. Okay, right here. So 10 is N. This here is X bar. And the sample standard deviation, that's called S. So let me put down a formula that we're going to use. It's just like the other one. When you happen to know the standard deviation, the proper population standard deviation, it works just the same way. So if I come here and I try to do sigma x bar, it's still going to be not quite sigma. Let's get that out here. It's going to be S over the square root of n. And I should probably be on the safe side here too. The way they generally put it is this, to indicate that it is derived from the sample and that it's not taken from the population itself. So let's put this information in. We have 1.8 divided by the square root of 10. All right, I've got that. Let's draw a picture of the situation. Now our sample mean was 17.7, that's to the right. And there's going to be my p-value. Let me get, now, instead of z, we're going to use t. That's going to equal, we'll have our, it's going to look exactly the same as before. Except now I'll change that down there to an S. So our x bar was 17.7. Our mu was 16.3. And then our sigma, 0.5692. 2.45959. Now that table has the t values to 3 decimal places. So if I round this thing to 3 decimal places, I'll actually end up with 2.460. Now draw a new picture just like you did before. This doesn't look any different really than the ones that we were using when we knew the standard deviation. I've brought up enough of the table to work this here. What they have here is the table has degrees of freedom. They didn't give us that. They gave us this in the problem, n equals 10. Well, the degrees of freedom simply equals n minus 1. So the degrees of freedom is 9. So that means I'm in this row. So what I try to look for, if I can, I try to find 2.46 in this row. So as I go, I notice it's between these two values here. So when I look here, if I'm doing 2, here, this area is between 0.05 and 0.02. So if you take the average of those two, you have 0.035. And that's the p-value. Now let's take a look at what our alpha was. So I usually do p-value versus alpha. Let me come back up here. The alpha, where'd you go, alpha? Here it is. Alpha is 0.05. So anyways, we have this. So reject H naught. So remember, use for two tails like this one was, stick to the second of these two rows at the top. Now that I think I have all the terminology set up, let me go ahead and label everything as I'm reading here. So N will be 15. The random sample has a mean of 40.6, so that is X with a bar over it. The calculated standard deviation is right there, so this is equal to S. And then if the average of all adults, so this is what we're going to put wherever the mu looks like it should be. And there is our alpha level. We'll need all of that. Let me get my H naught and my HA then. A physician claims that joggers' maximal volume oxygen uptake is greater than the average of all adults. A random sample gave us a mean of 40.6 millimeters. The average of all adults is 36.7. So let me see, is greater than is the phrase I'm looking for. So then I know that this part is going to say mu is greater than 36.7. And then the other one will be mu is less than or equal to 36.7. This here is the claim. And it will be a right-tailed test. Let me draw a picture. The sample mean was 40.6. Let me get the t-score. The x-bar, 40.6. The mu, 36.7. And I have yet to get the standard deviation for this. So remember that S sub x with a bar over it is equal to S divided by the square root of n. So S was 6, n was 15. I put that in there, 1 point. .517. Here I'll round my t-values to 3 decimal places because that's all the number of places in the table. Now, before we can use the table, I need the degrees of freedom. So up here, we have a sample size of 15. So the degrees of freedom is equal to n minus 1. So that's equal to 14. Here I brought enough of the table to see. We have degrees of freedom of 14 and 2.517. So let me go to the 14 row. And I will stop when I get once I get 2.517 trapped between two numbers, right here. There's our possibility. Since this is one-tailed, we're looking at these two numbers right here. So I'm going to take the average of those two, 0.025 plus 0.01 divided by 2. That equals 0.0175. So remember, this is our p-value. And it was going to equal 0.0175. Where is my alpha in this problem? Let's see if we can find that. Alpha is 0.05. So p-value, alpha, we see that alpha is greater than p, so that means that we reject H naught. Right here we have the average cost for teeth straightening is approximately $5,400. A nationwide franchise thinks its cost is below that figure. All right, so they told me this. My HA, they think that the average cost is below $5,400. So that means that forces H sub 0 to be greater than or equal to $5,400. So here's the claim, and it's a left-tailed test. So remember, your t-value is going to be negative. All right, what else do we have here? A random sample of 28 patients, so that's n. The average cost, a random sample of 28 patients. So this here is our x bar, and the standard deviation here is our s. And we're testing at alpha equals 0.025. And finally, I see the less than here. Let me get this number before I do anything else, since I'm thinking about it. We're going to have, where did S go? 629 divided by the square root of 28. 118.8698. All right, let me get my picture. The middle of this thing is at 5,400. We have 5,250 is to the left of that. Now let's get our t-value. Remember that equals x bar minus mu of x bar divided by s of x bar. So x bar is 5,250 minus 5,400 divided by 118.8698. Negative 1.262 if I round to 3 decimal places. Let's draw a picture. And let's see what the p-value turns out to be. I've brought up the relevant part of the table here. The reason why I'm bringing up this section for the degrees of freedom, we had n was equal to 28. So the degrees of freedom is equal to n minus 1, which is 27. So I'm looking at across this row here, and I'm trying to find 1.262. They don't have negative numbers in here. So find it between two values. If you look, I think these are the two that we're going to find it between, 1.057 and 1.314. And right here are my two values that I'm going to add together and then divide by 2. So this will be 0.125. That's our p-value. And so, p-value versus alpha. I think I did write, no, that's right, 0.125. Seems like a large number. My alpha were equal to 0.025. We see that p is greater than alpha, so we do not reject H naught. In this problem, they literally give us the sample to use, so we have to compute x bar on our own. So basically, you take these 7 numbers, add them up, and divide by 7. I don't care where you do this, in your calculator, in Desmos, whatever. It's easy enough to do. Let me get that information. I get 50,363.5714. Of course, I'm also going to have to put those into Desmos. I think that's probably the easiest things to put them into Desmos, because you're going to have to use your calculator or Desmos to figure out the standard deviation as well. In Desmos, I've got the numbers here put in. Remember, if you want to put in just a list of statistics, to use the square brackets and to separate the values by commas. Obviously, do not put commas in these numbers themselves, or it will ruin everything. So once you hit enter, you can do stuff with that. I think one of the commands is stats, and then I can just choose D, and it gives me a bunch of stuff here. That's not all that I wanted, though. It gave me Q1 and all that. I think I better get something else. So let's pop over here into functions and see what we've got for... Oh, here we are. Standard. Okay. I don't want it inside of there. Let me choose it again. Standard deviation. Put in your D. And there we have it. And I think, if I'm not mistaken, it copies that. So I'll bring that over in that format. Here's my sample standard deviation. Actually, what I'll do is round it to 4 places. So we'll just go to 4 decimal places on that. Then I'll need to do S sub x. That'll be the 1113.1594 divided by the square root of... Now let's see how many people were in here. Here's our alpha. We have an n of 7 for 20.7347. And let me get my H naught and my HA. So while we're here, oh, there's 7. The n is 7. I hope you can see. You just count them up. So the degrees of freedom is going to equal 6. So we see the term greater than 50,000 words. So we know the second place, mu, is greater than 50,000. That's the claim. And this is right-tailed. So this claim up here must be mu is less than or equal to 50,000. let's see, our sample was a little bit more than that. I'll just say this is X bar right here. That's this guy. Now let's go get my t value. My X bar was 50,363.5714. And our S sub X bar is 420.7347. I get 0.864. Let's draw a picture. And let's go see what the table tells us. All right, here should be enough of the table to tell. I can't even read what I wrote there. That was 0.864, 0.864. We have this last row here is the degrees of freedom equals 6. I'm going to look for numbers that 864 is between. And it looks like these two numbers right here. Since it's a one-tailed test, I'm looking at these two numbers, and I want to average 0.25 and 0.2. So if you put those together, you'll get 0.225 for an average of those two. Now, so my p-value equals that. Alpha, on the other hand, was 0.10. And we can see that the p-value is greater than. So do not reject H naught. Okay, here we have information about internet visits or sites that they visit. We're concerning 36 internet sites a month average, it looks like. A random sample of 24, that's going to be our N. A sample mean of 42.1, there's our X bar. And a sample standard deviation of 5.3, that's S. And here is alpha. So let's take a look. Well, let me get my H naught and HA while I'm here. So I see the word, this differs from. So what we need then is mu differs means does not equal. So does not equal is always go in the second row. It does not equal 36. Of course, then this would be mu equals 36. N equals 24. So the degrees of freedom will equal 23. And then S sub X bar, that'll be S over the square root of N. S was 5.3 divided by the square root of 24. I get 1.0819 for that. Let's draw a picture. This was the claim, and it's two-tailed. So the middle is 36 here, and our sample mean was 42.1, like so. Let me get the t-value. I get 5.638. So time to consult the table. Use the degrees of freedom, row 30 or 23, two tails. Well, I've got some of the table up. Our degrees of freedom were 23. So I'm in this row, and I'm trying to find 5.638 in that row if possible. So as you'll notice, as we go here, the p-values get smaller and smaller and smaller and smaller and smaller. What that means is that the p-value is less than any of these numbers up here. So since this is two tails in particular, the p-value is less than 0.001. It's off the chart, basically, very insignificant. In fact, this p-level is going to probably be less than any alpha value you could imagine. Let's take a look at our alpha and see what it was. The alpha was 0.01. So you have alpha is 10 times the size of 0.001, and even that's bigger than p. So the p-value is most definitely less than alpha. That means that we reject H naught. Here's one last example, and I can't help but notice that we're going to have to compute the mean on our own. First, let me count how many values we have. Well, it says 8 workers. Let me count that out. 1, 2, 3, 4, 5, 6, 7, 8. So n equals 8. The degrees of freedom equals 7. And what I need next are x bar and s. So let's get those. I'm going to throw these things into Desmos. Here I'm going to come back and change my letter D to the numbers that are in there. I've adjusted my backspace through here. We start a bracket. I got 8. Remember to separate these by comma. 12, 1, 5, 6, 1, 9, 13, 2, and finish. That's an 8-element list like it says. Good. Now we pull this up. I get the standard deviation and the mean. 8.25. I think I can remember that one. Let me copy the standard deviation though. There's my standard deviation, and x bar was 8.25. So I'm going to use 5.0639. That'll be the standard deviation that I use while I'm here. S sub x will be 5.0639 divided by the square root of n. And, well, we have 8 people, so that'd be 8. I get 1.7904. Let's get a picture. The mean that they're checking us out for has an average. So the U.S. Bureau, that's what they think. I am really doing this out of order here. To see if the average is correct, can it be concluded that the mean is? So that's an equal sign. Mu equals 9.2. And so the equals goes in the first. That is the claim right there. And we have a two-tailed test. Okay, so ours then, we are, the 9.2 is here. 8.25 is to the left. And we do that. Let's get a t-value on it. 8.25 minus 9.2 divided by 1.7904. negative 0.531. Another picture. All right, taking the table down, since we need our degrees of freedom is 7, I ended the table at 7. So that's the row that we're going to want to be on here, is the last row that I have. And negative point, now remember, we're looking at 0.531. So that's between here and here, between the first two values. Now this is two tails, so look at this. We're going to average 1 and 0.5. That is 0.75. So the p-value equals 0.75. Alpha equals, well, alpha is definitely going to be smaller, whatever it is. Where's my alpha at? Alpha equals 0.05. It's clear that the p-value is greater than alpha. So do not reject H naught.